So previously we have talked about why we need automation in spin qubit arrays or quantum dot arrays, and we've seen that as the number of gates scales, it becomes quite hard to tune them by hand to set n voltages, which you may have to increase or decrease, and by trial and error, by hand. And so we really need automation that will allow us to do some more interesting experiments than just keep tuning these devices. Secondly, we heard that there are a number of things you can do to recognize whether a device is good or bad. You can check gates, you can check the action of the gates on the quantum dot, you can compare that with your design and your lithography. And later on, you can look at the pattern of the transport or the charge sensing across your array to see whether your dots and your electrons are in the single electron or in the double electron or in the triple electron regime. And the pattern in your current or reflectometry or charge sensing, whatever it is that you're measuring, this pattern holds a lot of information about what the occupation of your array is. Another thing that you can do based on a paper that recently we published at the University of Copenhagen, tried to do another level of automation, which was that once you have tuned yourself to the let's say double quantum dot regime, where you have, as shown here, you have two quantum dots that each have one electron or more in them. And what you can see here is that, as we looked at in the previous video, you are going to have a pattern like a honeycomb, especially if you have allowed these dots to interact and have not completely made them into two single dots. Uh, this kind of honeycomb pattern, as we again discussed before, has certain lines which are more coupled to the X and Y voltages, which enable you to load electrons into the array. For example, going along the V1 axis, you see that you will be going from 0, 0 to 0, 1 to 0, 2, i.e. you're loading in the right dot. On the y-axis, however, you go from 0, 0 to 1, 0 to 2, 0, which means you are loading electrons on the left dot. And if these interdot transition lines, as we saw before, are special because they are where you go from the 1, 0 state to the 0, 1 state. For example, this means you are moving an electron from one quantum dot to the other quantum dot. More interestingly, you can also go from the 2, 0 to 1, 1 state, which means that in the 2, 0 state, both your electrons are on one quantum dot, while in the 1, 1 state, you have one each in the two different quantum dots. And so by going to the boundary of these two states, you are just making those two overlap their wave functions, and you can then separate them, and you can see that they have rotated each other by a given amount, and this would be a 2-qubit operation that you are performing. So we can see that the really important parts of this pattern are the lines where you load and unload your array, and also the areas of wave function overlap, which are these lines that kind of make the other sides of the honeycomb. And we essentially care about only the boundaries. We don't really care about the bits inside and outside. However, when we measure these diagrams, we would always measure all of this pattern. And this is, in some sense, a waste of data and time. And so maybe there's a better way in which a computer can help us to measure this without needing to measure the whole thing. One of the ways that you would normally measure these things is to do a raster scan measurement. You would set the voltage on the x-axis. On the y-axis, you would measure a point. You would then move to the next point, and you would repeat the same thing for the entire picture. Instead of measuring that entire picture pixel by pixel, you can also do something like send out array, where you think you will gather the most information. So instead of going line by line, you send out array, maybe you send it out in all directions, for example, in a kind of slightly cheesy animation, you are now exploring the boundary of your system. And what happens here is that you only measure one point, which is at the boundary of your system. And then the data you gather would only be the red points, which would enable you to find the boundary, where, as we discussed before, this line is loading into one of the dots, this line is loading into the other dot, and this line is where you have this interaction between the 2, 0, and 1, 1 states, which could perform a quantum gate. So this is a good way to go. However, you don't need to send out your arrows in every direction. This seems to be also not as efficient as we could go, but you could use an algorithm instead to find this boundary. So the task that we gave to our computer science collaborators is using as few of these line searches or arrays, you should gather enough information to learn with high confidence the 1-1 boundary. And the essential thing that you do, which enables this, is that each array that you send out uh, encounters generates 2 points as it encounters this boundary. 1 point can be inside and 1 point can be outside, and with reasonable certainty. And let's say our chart state boundary that we want to figure out is a square. This can be called the ground truth in the language of mathematics. But the computer, of course, doesn't know this ground truth. All it sees is these points that you generate as you send out the rays and measure 1 point at the boundary. The computer, what it can do is that it can guess at the best boundary that fits in with the known information. For example, given these 3 points here, it can guess at this boundary or it can guess at this straight line boundary, one of the two. So what it decides to do now is send out more rays such that it gains some information that enables it to rule out one of the two options. And now it keeps sending out more rays until it's reasonably sure. Of course, to our eyes, this doesn't look like much. The human eye could probably draw some complicated figure that blocks out, that does the inside-outside classification of this. However, the computer can now do a series of fits and use some classic ML tricks and figure out that actually the linear convex polytope, which is what we can reasonably expect our chart state boundaries to be, was actually a square. And so it presents it to us in much less time than it would have taken us to measure full raster scan and figure this out for ourselves. We found that it can find the boundaries very easily on a real device. On the left is a picture of the device. This was made at CEA-Leti, which can make industrial foundry-like devices, where the quantum dots were located under V1, V2, and V3, which was empty for this particular picture. Note that we have superimposed this on a raster scan to check that it actually found the right boundaries. And indeed, it also found the small boundaries at the corner, which indicate the ones you can use to make a quantum gate, perhaps. And it can also do it in 3D. In 3D, it was too hard to measure the ground truth brute force. So we will just show you the picture of the boundary that the AI found, and we are reasonably sure that this is now correct. And it takes 12 minutes or so versus 2 to 3 days brute force, if at all your device is stable. The question that remains, of course, is that these are kind of demonstrations that have worked on smaller scale devices. And so the question we can ask is, will these methods scale to larger arrays? For example, the 4x4 array that has recently been shown by TU Delft. And the end message maybe is actually that we need to keep looking for the best methods to tune and operate qubit arrays. And we also need to make these arrays more uniform so that we need fewer and fewer gate voltages to tune them.